Hey everyone, welcome back to the deep dive. We're about to take a deep dive into something you think you know, but trust me, this is going to blow your mind. We're talking electric charge.
Yeah, electric charge. We're going way beyond sparks and static cling, though.
Definitely. We've got some really fascinating source material here that takes us all the way from the fundamental nature of what charge is to some pretty wild ideas about the future of energy.
We're not just talking about plus and minus signs here, though. We're talking about how energy itself gets organized at the most basic level.
Right, because everybody kind of knows that electricity is the flow of electrons, but these sources are saying that charge is way more fundamental than that.
Yeah, they're saying it's not just a property. It's actually like an emergent property. It comes from how energy is structured, by information. It's like the pattern of energy.
Okay, so we got to unpack this whole information structure thing because it's pretty central to everything we're diving into today.
For sure.
One of the sources explains it as this asymmetry, right, in the information structure of material.
Exactly.
So some materials have this positive affinity, they really want to get rid of electrons.
They're like, get out of here, electron.
Exactly. And then other materials have this negative affinity, so they're electron magnets.
Pulling them in.
Yeah. And it all comes down to the configuration of their electron clouds, which, as we know, isn't random, right?
No, absolutely not.
It's this physical representation of all the information that's structuring how those atoms are interacting with each other.
Right. So it's not just about how many electrons something has, but it's about their arrangement and their behavior, their patterns and how they move around within the atom.
Okay, so this is a bit mind-bending, but one of the big takeaways from these sources is that charge is actually how information organizes energy, at the quantum level.
Yeah, think about it. At the level of atoms and electrons, the rules of energy are different. It's quantum, right? And what these sources are saying is that the arrangement and interaction of those tiny particles, those electrons, that's the information. And that information is what determines how charge behaves.
Wow. Okay, so to understand a material's affinity for positive or negative charge, the sources point to a few things.
Mm-hmm.
First, we've got electron density distribution. So, how tightly those electrons are held within the atom's influence.
Right, some atoms hold on to their electrons with a really tight grip.
Exactly. Then you've got the resonant coherence of atomic bonds.
This is about how stable and synchronized the movement of electrons is within the material structure.
Okay, so basically, how well behaved are those electrons?
Pretty much. And the more coherent the system is, the more ordered and predictable its behavior.
Got it. And lastly, we've got the material's response to external charge fields or its polarization, so how its internal charge distribution changes when it's exposed to an electrical influence.
And this is all connected, right? It's not like these are separate things happening.
Right. Yeah, it's all part of the same underlying information architecture of the material. It's like the blueprint for how that material interacts with charge.
Exactly.
And a great example of this is the triboelectric series. You've got air, glass, and wool at the very positive end. They lose electrons easily, and they have low information density.
Yeah, they're like the free spirits of the material world, always ready to let go.
Then in the middle, you've got your more neutral materials like wood and cotton.
Mm-hmm.
They're pretty balanced in terms of their electron behavior.
Yeah, they're just chilling, not too eager to give or take electrons.
And then at the highly negative end, you've got your gold, copper, and graphene. They're all about attracting those electrons. They have high information coherence.
Yeah, think of them like the super organized, efficient types, everything in its place, and they want more electrons to add to their collection.
Okay, so the big question here is why? Why do these materials have such different preferences for charge?
And the sources make a really strong link to information density and coherence to explain this.
Right, like with air, for example. Air molecules are constantly moving around in a random way.
It's a very chaotic system, low coherence.
Exactly. It's like a big party where electrons are constantly bumping into each other and getting knocked off.
Exactly. It's easy to lose an electron in all that chaos.
But then you've got something like gold. Its atoms are arranged in this incredibly ordered crystalline lattice.
High coherence and high electron density.
It's like a perfectly choreographed dance where everything is in sync.
Right, and because everything is so well organized, energy can flow through it really easily.
Like a superhighway for electrons.
Exactly. And that organized structure makes it really good at attracting and holding on to electrons.
Okay, so we've talked about information structure, electron affinity, the triboelectric series. How does all of this connect to actual technology?
Well, one of the sources takes all of this fundamental knowledge and applies it to something we all know, the light bulb.
Oh, interesting.
Yeah, it uses the story of Thomas Edison and his invention of the light bulb to illustrate how understanding charge coherence and information density could have changed history.
Okay, so how does this all tie into Edison and the light bulb?
Well, they reframe electricity as a controlled flow of charge over time.
Okay, yeah, that makes sense.
Right. And they emphasize the importance of voltage gradient, the material's information coherence, and time itself.
So basically, how well the material can maintain that flow of charge over time.
Exactly. And the argument is that if Edison had understood these principles of charge coherence and information density, he could have invented the light bulb a lot faster.
Really? Like, he could have skipped all those thousands of failed experiments.
Potentially, yes. Because instead of just randomly trying different materials for the filament, he could have used his knowledge of charge coherence to pick materials that were more likely to work.
So instead of just seeing a filament burn out, he could have understood why it burned out.
Exactly. He could have understood that the materials he was using had low coherence, which meant they couldn't handle the flow of charge effectively.
And that led to all that wasted energy and, burnt out filaments.
It's fascinating, isn't it?
It really is. And it's not just about filaments, right? The source also talks about how Edison could have improved the efficiency of his early vacuum tubes.
Right. Instead of just relying on mechanical pumps to create a vacuum, he could have explored charge coherence techniques to actively repel the remaining air molecules.
So using charge to create a better vacuum.
Pretty much.
Yeah.
And by understanding how charge interacts with different gases based on their information density, he could have created a much more effective vacuum more quickly.
Wow. That's amazing. And like you said, it's not just a history lesson, right? These principles apply to modern technology as well.
Absolutely. Understanding these fundamental properties of charge helps us design better energy systems in so many ways. Well, for starters, we can choose the right materials for energy harvesting, like pairing a highly negative material like graphene with a highly positive material like silica to create a more efficient energy flow.
Okay, that makes sense. And what about energy storage?
Well, we can use coherence principles to reduce energy loss during storage.
Right. So like using materials with a highly coherent structure to create more efficient batteries or capacitors.
Exactly. Like graphene-based supercapacitors, for example.
And even controlling the structure of materials at the atomic level to manage charge behavior.
Right. It's like we're becoming architects of energy, designing materials from the ground up to do exactly what we want them to do.
That's incredible. And speaking of incredible, one of the sources even talks about extracting energy directly from the atmosphere.
Oh, yeah, that's like straight out of science fiction, right?
It really is. But apparently, it's not as far-fetched as it sounds. The atmosphere is filled with this incoherent, free-floating charge.
It's like a sea of untapped energy, just waiting to be harnessed.
And the key to tapping into that energy is using materials that enhance coherence and create those charge gradients.
Yeah, like setting up a pathway for that chaotic energy to flow into a more ordered system.
Exactly. And the source even gives some examples of how we could do this.
Yeah, like building towers made of these special nanostructured materials that are designed to draw in electrons.
Wow. And using resonance principles to create these self-sustaining, oscillating charge fields. It's mind-blowing.
It is. And it raises the question, if we can pull energy from the atmosphere, what does that mean for the future of energy?
That's a great question. And speaking of the future of energy, the sources also talk about this idea of coherent energy storage, which goes beyond batteries as we know them.
Yeah, like supercapacitors that store charge in those highly structured atomic lattices we talked about earlier.
Right. So instead of relying on chemical reactions, they're using the structure of the material itself to hold the charge.
Exactly. And because they're using materials with such high information density, they can store energy for much longer periods with almost no loss.
That's amazing. Like, imagine a world where batteries never degrade.
It would revolutionize everything.
And the source even mentions this idea of self-recharging materials that can continuously scavenge background charge and store it.
That's like something straight out of a sci-fi movie.
It really is.
But, it makes sense. If we can understand and control charge at this level, who knows what's possible?
Totally. And speaking of charge, we can't forget about the most familiar form of charge, static electricity.
Oh yeah, that annoying zap you get when you touch a doorknob after walking across a carpet.
Exactly. But the sources explain that it's actually more than just an annoyance. It's a demonstration of how charge imbalance can create huge potential differences.
Yeah, and that zap is actually the release of stored information in the form of energy discharge.
So it's like a tiny little capacitor that's been holding on to all that potential energy.
Exactly. And the sources even talk about how we can harvest that static electricity to power our devices.
Like triboelectric floors that generate energy from footsteps, or wind-powered charge sheets that capture energy from the movement of air.
Yeah, imagine a world where we're generating energy from everyday activities.
It's amazing. And it all comes back to this idea of charge polarity, positive, negative, and neutral.
Yeah, and the sources make it clear that these polarities aren't just arbitrary labels.
Right, they emerge from how information density structures the flow of energy within a material.
Exactly. Like air, for example.
Yeah.
It has low electron affinity and high decoherence because its molecules are moving around so quickly.
That's why it tends to have a positive charge.
Right. And then you've got neutral materials like wood, where the charge flow is slower and more balanced, so they maintain neutrality.
And then at the other end of the spectrum, you've got highly negative materials like gold. They have a really strong grip on their electrons and a highly coherent structure.
So they maintain their negative charge. It all makes sense when you think about it in terms of information and energy flow.
It really does.
Yeah.
And the sources don't stop there. They even explore some pretty radical future applications of this technology.
Yeah, like using charge to create coherent energy fields that can power our devices wirelessly.
Or even potentially manipulating gravity with charge.
Like what?
I know, it sounds crazy, but the sources reference something called the B-filled-Brown effect, which suggests that it might be possible.
Wow. And then there are applications in bioelectricity and healing, using charge to optimize cellular energy production.
And even using charge for water purification, like electrostatically separating contaminants from water.
It's like we're just scratching the surface of what's possible.
It really is. And for anyone who wants to explore these ideas a little more hands-on, the sources suggest some cool DIY experiments.
Oh, I love that.
Yeah, like building a simple triboelectric generator using Teflon and wool.
Or experimenting with atmospheric charge collection by setting up a graphene-coated plate and measuring the voltage at different heights.
And even exploring graphene supercapacitors to see how well they retain charge.
It's a great way to see these principles in action.
Absolutely. So let's wrap up here. The big takeaway from all of this is that the behavior of electric charge is not random.
It's governed by these fundamental principles of information density and coherence.
And understanding these principles opens up a whole new world of possibilities for energy technology.
It's like we're on the verge of a new energy revolution.
So let me throw this out to our listeners. Imagine a future powered by free atmospheric charge, highly efficient static electricity harvesting, or near-perfect energy storage. Which one excites you the most? And what are the implications, good and bad, of such a radical shift in how we think about energy?
What new questions does this understanding of charge raise for you? We'd love to hear your thoughts.
This deep dive has been a wild ride. Thanks for joining us. We'll see you next time on The Deep Dive.